make this your whole, make that your a sub n, okay, or a sub k or whatever, a sub n, a sub k, and then take the limit as, but do it this way. Do this version of the ratio test. Take that limit and then call that L, and it will, and then it converges when L is less than 1. So do that version. Okay.
Okay.
This one, this is actually, so this one ratio test is not going to work. Okay, can't do ratio test there. Or I guess you could do ratio test this way. Yeah, that would also work. You could do the same thing there, but make all of this a sub k. But the other thing you could do is, this is a geometric series. So if you have r to the n, okay, this converges when the modulus of r is less than 1. Okay, so you can think of all of this inside here as being r, and then figure out where the modulus of that's less than 1. And that would,
Okay.
that would work. That would be the same as doing this, really.
How about number 2 though? Like, how do I find a function that is?
Okay, so for number 2, does this look familiar to you guys at all? Here, I'll do this. Okay, this one right here. Okay, so for this one right here, you know that when this converges, this is 1 over 1 minus r, right? So you can like use that. Okay, for this one, I'll give you a few hints, okay? Do this. Write out some terms. Okay, so first just write some terms out. So like set k equal to 0, because it starts at 0, right? Set k equals 0, that would be, so when k is 0, you've got z over 1, so just z, right? And then when k is 1, you have, this is going to be z cubed over 3 factorial, right? Okay. Okay, z plus z cubed over 3 factorial. Okay, so now do you recognize this at all?
Sine.
But anyways, I want you to do this. Compare with e to the z and e to the negative z. So expand these two out and see what you get, but just like write down terms. Okay, so expand these two out, see what you get. Okay?
Okay.
So those are big hints right there.
Okay.
Okay, is there anything else? Okay, let's go ahead and cover the new things. Let's see, where were we? Let me find the place here. Okay, so we talked about the identity principle. So if you have like infinitely many zeros in this compact place, then your function has to be identically the 0 function. Okay, So there's that. That's the identity. That's the identity principle. Let's see. Oh yeah. Okay. So we talked about other stuff. Okay. Good. We have talked about other things. So let's see. Where are we now? Okay. So the maximum modulus principle. Okay. So this is really important, or somewhat important. Okay. Suppose f is holomorphic and non-constant in region Hg. Then the modulus of f does not attain a weak relative maximum in G. And usually this sounds kind of weird at first. Whoa, it doesn't attain a maximum in the region. But what it really means is that the maximum is going to be on the boundary. Okay, it's going to be on the boundary. So this is it. So the maximum in the region is on the boundary. So like, if you have, this is your region right here. Okay, it's holomorphic inside. It has to be holomorphic everywhere in there and non-constant. Then it's not going to attain the maximum inside. The maximum is going to be somewhere along the boundary, not interior. And this one is sort of like, you can kind of justify it this way. You can kind of, hopefully, okay, so let me just do something really quick that might help it make some sense. If you take a point inside here, okay, and it's interior. If it's interior, then you can draw a circle around it that's also going to be completely inside. And let's say that point is W. Okay, so the function f of W, according to Cauchy's integral formula, f of W is actually just going to be, let's see, you set k equal to 0 to apply that. So it's 1 over 2 pi I times the integral around that, in this case, we're going around this circle here. So centered at W of radius R of f of z over z minus w dz. So it's that, okay? Now, if you parameterize this circle, okay, do you guys remember how to parameterize this circle?
W,
well,
R, E.
Yeah, it's W plus R e to the IT, or theta, where t goes from 0 to 2 pi. Okay, so if you set that up, you get 1 over 2 pi I times the integral from 0 to 2 pi, by these limits here. This is f of W plus R e to the IT over, and then down below, what you're going to get is this z turns into W plus R e to the IT minus W. Okay. And then your dz is the derivative of this, which is I R e to the IT dt. Okay, so now this is my favorite part. There's a lot of canceling. That cancels with that. This R e to the IT cancels with this R e to the IT. This I cancels with that I. And essentially what you end up with is f of W equals 1 over 2 pi times the integral from 0 to 2 pi of f of W plus R e to the IT dt. Okay, so that means that the value at the center point is equal to the integral. Okay, these values are these represent the values of f on this circle. Okay, now you're integrating from 0 to 2 pi, and you're dividing by 2 pi. Okay, so this is basically telling you that f of w is the average value of points on the circle, of the values on the circle, I'm sorry. Okay, so if this point in the middle is the average of all these values on this circle, then there's no way it can be larger than all of them. Okay, it can't be larger than all of them. Its modulus can't be larger than all of them because it's the average of all the points on the circle. So there's no way that its average can be larger. Okay, so that's the maximum. That's kind of a justification for the maximum modulus principle. Now, let me give you an example. So, for example, we're going to take f of z equals z squared plus 3z. Okay, and so let's say that we were supposed to find the maximum. Okay, let's find the minimum and the maximum of the modulus of f of z on the circle whose center is at 2 and radius 2, whose center is 0 and radius 2. And, well, that z looks kind of like a t, but I'll make it look like a z now. Okay. So, for the maximum, then we can apply the maximum modulus principle, and it has to happen on the boundary. Wait, okay, so what I meant to say is the disk. The closed disk, just to be sure. Okay, so this disk is, you come out to 2, 2i, negative 2, and down to negative 2i, and this, and you're also including the inside. Okay, so what it's saying is that the maximum has to be on the boundary. Has to be on the boundary, because this is holomorphic everywhere. This is an entire function. On the circle, so it has to be on the circle, which is the boundary. Okay, so now, if somebody want to guess what the maximum would be? What's the maximum value of this on this circle? And what point would give it to us out of all these points on the circle? You should be able to guess it. Or you might be able to guess it, I guess.
Do we take the modulus?
What's the modulus? So the modulus, well, let me give you a hint, okay? By the triangle inequality, this is less than or equal to the modulus of z squared plus the modulus of 3z, right? But if these are on the circle, then this is going to be 2 squared plus 3 times 2. So that's going to be 10. So the most you can ever get, because of the triangle inequality, the most you can ever get is 10. But the question is there a point here that will give you 10? Is there a point on the circle that will give you 10? Okay.
Yeah,
the same.
2.
Yes, 2. F2 is 10. Because it's going to be 2 squared plus 3 times 2. That's 10. So the maximum is 10. You can be sure of that because you can't get more than 10 because of the triangle inequality. Now, let me just point something out really quickly in case anybody got confused about this. Another way of saying a circle is by saying the modulus of z equals 2. Okay, that's another way of saying the circle centered at the origin of radius 2. Modulus of z equals 2. And so that means that the modulus is anywhere on this circle, the modulus is 2. Anywhere in this boundary. Okay, so now the other question, the minimum. The minimum of the. Can anybody want to guess that?
Zero.
0, yes. What point gives you 0?
0.
0, right? So the minimum is 0. And that happened right here, right? That happened in the middle.
Yeah.
Okay, now, there is a minimum modulus principle right here, which is right here as well. Corollary 8:19. Okay, so here it says, it starts off by saying, suppose f is holomorphic and non-constant in the region, then the modulus does not attain a weak relative minimum at a point A in G. And so you might be thinking, at this point you're thinking, whoa, we just did a problem where the minimum happened inside G, right? But it says unless f of A equals 0. Okay, so that didn't count. Okay, because we found a point where it's 0, then that didn't count. Okay, and the reason for that, the reason for this is that if f of A is if f of z is not 0 for all z and g, then you can form another function called that g of z is equal to 1 over f of z is holomorphic and non-constant. Okay, so let me go through that again. Okay, so if f is holomorphic and non-constant, and f of z is not equal to 0 for all z and g, then g of z, which is 1 over f of z, is holomorphic and non-constant. And so then you can apply the maximum modulus to g of z. But the maximum for g would be the minimum for a. Okay, so the minimum for f of z would be the maximum for g of z. Okay, so let's do, there we go, that's the blank page. Okay, let's do another exercise, another example. And we'll take f of z equals z squared minus, we'll say minus 5, okay? Okay, so find the maximum of f of z and the minimum of f of z, or the modulus of f of z, on, this time we'll have the same set again. The closed disk centered at the origin of radius 2. So again, it goes through these points here. And you're including inside. Okay, so the maximum, anybody want to guess what the maximum would be and at what point it would happen? So we know, so first of all, we know that it has to happen on the boundary, right? Because of the maximum modulus principle. But what point on the boundary will make this as large as possible? Okay, so by the triangle inequality, it has to be less than or equal to this, right? And what's this on the boundary? What's this?
4.
That's going to be 4, right? And then this one is just going to be 5. Okay, so the most it can ever be is 9. Okay, so can we find a point where the modulus is 9?
Yeah, 2i.
2i, right? Okay, so 2i gives us, that's going to give us 2i squared minus 5. So that's going to be -4 minus 5. That's, the modulus is 9. Yes. So 9 is the answer. At z not equals 2i. Okay, now, what about the minimum? First of all, could the minimum happen inside? Okay, so according to the minimum modulus principle, what's the only way that a minimum can happen inside? The only way is if f of z is 0, right? So the only way is if f of z is 0. So if we set this equal to 0, then we're gonna get plus or minus √5, which is outside, right? There's √5 and there's -√5. So those points is where the function is, those give you 0. Okay, so that means that it's not going to happen inside. It's got to happen somewhere on the boundary. Okay, so what value do you think will give us the minimum value?
Is it the same as maximum?
What's that?
I thought there's no minimum value.
There will be a minimum value on the boundary. And one of these points somewhere is going to give a minimum value for the modulus of this. Okay, so
2.
what's that? 2?
Mm-hmm.
Yeah, that works. So that's going to be 2 squared minus 5. That's going to be 1, right? Also, -2 also gives you that also gives you 1 as well, and that makes sense. They're closest to these points here. And also up here, -2i will also give you the -2i will also give you the maximum of 9. We also know that if you take z squared minus 5, this is going to be greater than or equal to the absolute value of the difference between these two. Which this is going to be 4. And that's going to be 5. So by the triangle inequality, the smallest that you can be on this boundary here is 1. And we got something that gave us 1, so that's 1. Minimum is 1 at 2 or -2. Okay, and this is the same thing right here. This could also happen. -2i will also give us the maximum. Okay, so that's the maximum modulus principle and the minimum modulus principle. Okay, so now let's go to something called Laurent series, and this right here is very important for the rest of the semester. Okay, so we're in chapter 8 now. When we come to chapter 9, if you understand this really well, then that will be very helpful. Okay, so a Laurent series is a series. So like a Taylor series goes from, so Taylor, that goes from 0 to infinity, right? And it's like C sub n z minus z0 to the nth power, right? It's like that. Okay, so Laurent series, it is essentially negative infinity to infinity of the same thing. Okay, so Taylor, Laurent. So it's just basically, you just can make it can go from negative infinity to infinity. Okay, and now a lot of times it's not written that way. Okay, so here's an example of the exponential function of 1 over z. So you know that the exponential is just, so here you know that the exponential function is just, of z, is just this, right? K equals 0 to infinity of z to the k over k factorial. Okay, but if you replace this z with a 1 over z, then you're going to get this. Okay, so the z gets replaced with a 1 over z, you get this. Okay, so that's a Laurent series, but it's not a Taylor series. Okay, and then it's perfectly fine to write Laurent series this way. That's perfectly fine, and typically that's what's going to happen a lot of times. So this right here is this is what this means. It goes from negative infinity to infinity. That's what that means, because this z represents all integers, negative and positive. So it's a double series of this form. Okay, I'm going to go over a really important example. Okay, so this is something you're familiar with. So 1 over 1 minus z, or hopefully. How do you write that in a Taylor series? Okay, we're talking Taylor series, okay? Taylor series. You guys remember what that is?
Z to the k.
Yeah, just z to the k. Okay, so this is the geometric series. This is really important. And this converges where?
When the modulus of z is less than 1.
Yes, where the modulus of z is less than 1. Okay, now, so let me draw a picture of this historic event. So here we have 1. Okay, so this one converges in here. So here's the thing. This function, this very same function, has a Laurent series, and that Laurent series is actually going to converge out here. It will diverge inside, but it will converge out here. Okay, so let me show you how you can get that. Okay, so we'll call this f of z right there. Okay, and we'll do Laurent series in red. So we still have this, it's the same exact function, but I'm going to manipulate it a little bit. I'm going to multiply the numerator and the denominator by 1 over z, like that. Okay, so that's going to give me a 1 over z in the numerator, and then the denominator is going to be 1 over z minus 1. Okay, now I'm going to factor out a negative 1 over z, and that leaves me with 1 over 1 minus 1 over z, like that. So I factor this guy all the way out. I factor a negative out of the denominator also. So this negative came from the denominator. And so I flipped the order of these. So it's 1 minus 1 over z now, instead of 1 over z minus 1. Okay, now, this negative 1 over z, we're going to leave that here for now. This part, it's of the form 1 over 1 minus r. So this is like our r there. So, so you have this series now. And this one converges when the modulus of 1 over z. So this 1 over z is like our r. So this is going to converge when that's less than 1. But that's the same as modulus of z greater than 1. So yeah, it converges everywhere out here. Okay, so here we have a representation. And we can pull this back in. So we can say that it is negative, I don't know, 1 over z to the k plus 1. Okay, so this is a Laurent series. For f of z that converges and the modulus of z greater than 1. Okay, so this is a Taylor series. This is also a Laurent series, by the way. So Laurent series is more generalized. It's more generalized than a Taylor series. So Taylor series are special cases of Laurent series where all of the negative ones are, where it just starts from 0 to infinity, and we've got up here. Okay, so now this is not really written in the form that you would of what I said right here, so that can be a little bit confusing because I'm like, okay, it's like this where you don't have like 1 over stuff, but it's still you know, it's a good way to write it. This is a good way to write it like that. Okay, so there's an example of Laurent series. Okay, and oops. Okay, so let's move on. Let me see here. I think there's some more examples I need to do for you guys. Okay, let me do some more examples. I'm gonna use up all my space. Okay, so let's let f of z be this function. So 1 over z plus 1 squared times z minus 2. Okay, and request is to find a Laurent series centered at z naught equals -1. Okay, so the example that we just did, it was Laurent series centered at 0. Okay, so this one was Laurent series centered at 0, which is going to be that's probably most of the time what's going to happen, because it's the easiest. Okay, but here we're going to center it at -1. But centering at -1 is not that big of a deal, because we have, this is already, okay, so when you see that it's centered at -1, then immediately you think, oh, it's like z plus 1, right? Your term should look like that when you see that it's centered at z naught equals -1, or if it's like centered at a, your terms are going to look like z minus a. Okay, so since it's centered at z plus 1, then this is already great stuff right here. So we don't have to worry about that. We only have to worry about this part. We don't have to worry about this one, the z minus 2. And so we need to figure out how to, so what you can do is manufacture a z plus 2. So you don't see a z plus 1. So this is z minus 2, right? But I want a z plus 1, so just put a z plus 1 there. Okay, and then what do I have to add here so that this and this are equal? So that is equal to that. What do I have to add here or subtract?
3.
3, right? Because 1 minus 3 is going to give me -2. So good, that's what you do. Okay, and then I really want that to come second. So I multiply both sides by -1, and then I have 3 minus, and this comes second right here. Okay, but I need a 1 right here. So if I multiply by the numerator and the denominator by 1/3, that would give it to me. In fact, let's pull this. We'll pull a -1/3 all the way out to here. Okay, so we have z plus 1 over 3 right here. And that, so you have 1 over 1 minus something. So that is, so what does that mean? So what's the series involving this one? What are the terms of the series?
Is that z plus 1 over 3 to the k?
Yep, exactly. Yeah, that's exactly what it is. So great. So now, so we've got it. So we just have to pull this stuff back in. So the numerator is z plus. So this is also z plus 1 to the k over 3 to the k, right? So we can pull the negative in. Now this is in the denominator, so this is going to be z to the k minus 2. Z plus 1 to the k minus 2. So this is a minus 2 right here. And then down here you have another 3 adding, so that's 3 to the k plus 1. And where does this converge? Well, it converges when this modulus is less than 1. Okay, or modulus of z plus 1 is less than 3. Okay, so now, but it's not going to converge where, well, this will converge there, but then if you add this part in, then it's not going to converge at the, it's not going to converge at the origin. Nope, it doesn't converge there. Wait, I'm sorry. We're centered at -1, so here we are at -1. It's not going to converge at -1 because you can't stick in, when you plug in z equal -1, then this is not going to work. You get 1 over 0, so that's no good. Okay, so the radius of convergence is 3, so come out 3 in all directions. Oh, it's not going to converge on the boundary. Okay, so it's going to converge everywhere inside here, right? Now, if you go back to here, that's another 0 of the denominator. So when z is 2, that gives you a 0 of the denominator, which we'll call a pole later, but we won't call that yet. We won't call it a pole yet, but we will someday. So we'll start calling that pole. So 2 is a pole, but we're not going to call it a pole. So 2 is a 0 in the denominator, and that's right here, right? So you have that Laurent series. Now, let me make a note here. And that is, you can find another Laurent series that will converge out here. So you can find another one that converges out there. That's possible. And the trick would be to manipulate this a little bit differently. Okay, so the trick would be this. So let me just kind of show you how you would do it, how you could go about doing that. Okay, so what you would do is you know that this part is, you know that's 1 over z plus 1 minus 3, right? So we got it to here. We got it there. Now, instead of just like flipping it this way, what you would do is you would actually multiply at this point, you would multiply by the numerator and denominator by 1 over z plus 1. Okay, so the numerator would become 1 over z plus 1, and then the denominator would be, that's convenient, that's all 1. And then you have minus 3 over z plus 1. Okay, so then this piece would go out and join his buddies over here. You have 1 over z plus 1 to the third power. And then you this part, then you would have 1 over 1 minus 3 over z plus 1, like that. And then this part can go into the power series, into a geometric series. That would be 3 over, what's that?
I'm wondering, why do we always want to make it look like 1 over c plus 1? Like
1 over that?
That's
when you want to do you want it to converge out here. Because when it's 1 over that, then that's going to converge for this less than 1, which is the same as k plus 1 greater than 3.
like
Okay,
even
so there's 2 different. What's that?
like even when we were finding the blue, when you're writing in the blue color, like why do we need to do this? I'm just wondering, can we just find the series from 1 over c minus 2? Why do we need to change it to look like 1 over c plus 1 minus 3?
Because we want to center it at this point. Okay, so the thing is, if it's centered here, then your series has to look like this. Your terms have to look like this. You have to have you have to have powers of z plus 1. So it's powers of z plus 1. So in order to do that, we need to get a z plus 1 there.
Got it.
Which is right here. So we need to get something like this. We need to get, what you're looking for is, basically, what you're looking for is 1 over 1 plus this, over 1 plus something. And you have to have a 1 there and a 1 there. And the something has to contain z plus 1 over something, or something over z plus 1.
Okay.
One of those 2. Okay. So and then if it's this one, it's just the blue. If it's this one, then it's the red. Okay, so notice that this form right here, I got it right there, and I got it right there. And then as soon as you got it, then you have this series. As soon as you got that, you got this series, because it's a geometric series. Okay?
Okay.
So we can call this R. 1 over, wait, I'm sorry. This should be a minus. Sorry about that, it should be minus. 1 over 1 minus something, 1 over 1 minus. Okay, also I made another mistake. This converges, this doesn't converge when z plus 1 equals 0, because that's right here at this point here. In general, see here. Let me do another quick problem. I'll just do it right here. Okay, so we'll go z plus 3 over z minus 1 squared, centered at z naught equals 1. Okay, this one right here is the only bad point is this one right here, is the one where it's sent, where you want to center your Laurent series about. Okay. So if you do this, how can we make this numerator the same as that one? What can we add? A 4, right? Because 4 minus 1 is 3. Okay, now we'll split this up with this over this, which is just going to be 1 over z minus 1 plus 4 over z minus 1 squared. Okay, and this right here is the answer. This is the answer. Okay, so this is a Laurent series centered at z naught equals 1. Because it's just this term over that plus another term over that. Okay, now let me explain something about how these work. I'll start to use this picture right here. Yeah, sure, why not? Well, maybe not. Maybe I shouldn't do that. This like tells you how to find terms, but this is kind of cumbersome in practice to do it this way, so I'm not going to really go down that path. But I wanted to say, I wanted to tell you about kind of a principle about this, about how of the Laurent series that you can find. Okay, so I'll just give you kind of a general example. Okay, so let's suppose that f is holomorphic except for singularities. And rather than like tell you what the singularities, so singularity is where it's holomorphic everywhere except that point. It's holomorphic around that point. You can find a neighborhood where it's holomorphic around that, in a neighborhood around that point, except at that point. Okay, so you can call that like a punctured disk, a punctured neighborhood. And so let me kind of draw the singularities. So we have a singularity there, and we have another one over here. And let's say we have another one. I'll just leave it at that. No, one more. We'll put one right here. Okay, so let's suppose that we're going to expand it in a Laurent series. And this time I'm just going to expand about the origin because that's the easiest thing to do. Now, we already said that if you do a Taylor series, then then that's going to the radius of convergence is the distance from the center to the nearest singularity. Okay. So we'll call that Z0. We'll call that Z1. We'll call this one Z2, and this Z3. Okay. And let's say that R1 equals the modulus of Z1. And let's say that R2 is the modulus of Z2, and we'll say that R3 is the modulus of Z3. So those are the singularities. It converges everywhere else. So this Taylor series converges modulus of Z less than R1. Okay? Now, the next thing that's going to happen is if you go to the next point, which is this one right here, you'll have this other region, and this is called an annulus. You're going to have a Laurent series that converges in this annulus, which is given by this. So you converge it right there. That looks delicious. It's like a bagel or a donut, even better. Okay, and then we go to the next one. And we have another outer circle. Oh, so this is like one of those donuts. This is like one of those pastries with this pastry stuff here, and then inside there's like this cream, and in the middle there's like this berry filling. Okay, so you have another Laurent series that converges in this one, in this kind of brown area. And then finally, you're going to have, let me see, what color can I use? I can use this purple. Okay, so then finally, you've got this outside part here. So you're going to have another Laurent series that converges for the modulus of Z greater than R3. So everything outside. Okay, and then these Laurent series are not going to be equal to each other, and then none of them are going to be equal to the Taylor series. They're all going to be different. Okay. So that's what happens with that. Okay, so let me do one more example, and then we'll continue on. So let's say we have sine C over Z. Okay. And then another way of writing this is that it has another way of saying that it's centered at 0 is to say it has powers of Z. Okay. So Laurent series of sine Z over Z that has powers of Z. Okay, so now what you can do is you got this 1 over Z here. You can pull the 1 over Z out, and then sine Z is going to be Z minus Z cubed over 3 factorial plus Z to the 5th over 5 factorial. minus z to the 7th over 7 factorial. Okay, and then that's 4 non-zero terms right there. 1, 2, 3, 4 terms. That's good. That's qualified as a good answer. And you just distribute this 1 over zn. So you get 1 minus z squared over 3 factorial plus z to the 4th over 5 factorial minus z to the 6th over 7 factorial plus ... Okay, so there's the answer right there. And then if I wanted Laurent series for g of z, which will be sine z over z cubed, then instead of dividing by z, I just divide by z cubed. So this would be 1 over, so the leadoff term will be 1 over z squared. This will be just 1 over 3 factorial. And this one will be z squared over 5 factorial. And this will be z to the 4th over 7 factorial. Okay? And by the way, this one right here is also a Taylor series. Okay. The only thing is, the only difference is right here for this, it's not defined at 0. When z is 0, this is not defined because you're dividing by 0. But this is defined, and it's just 1. When z is 0, this is just 1. And it's a Taylor series, and this is an entire function. This is entire, by the way. Holomorphic everywhere, even at 0. Because this one's not, though. This is not holomorphic at 0. It's not even defined at 0. So yeah, this is not defined at 0. But if you look at it if you look at the corresponding power series, this is defined at 0, and it's 1. Okay. So that's some examples of that. Now we'll go on a little bit further to the next page. This right here, this corollary at the bottom, this corollary 827, this is actually tells you why this is so important for, they're one of the reasons why this is very important for complex numbers, and which we get into chapter 9. And that is that before, if you can, so here's the thing, if you can split it up into a Laurent series, and I'll try to give you an example. So this in particular is what we're looking at. But let me try to explain this on this page here. I'll give you a little bit of context here. So let's suppose that you have a function, and so let's suppose f of z is holomorphic in a region G, but except for at z naught. Okay, so here's z naught. And then let's say this right here is, let's say that G is like this region here. So G is right there. Okay, and then let's suppose that, okay, so if, let's say we have a curve. The next thing is we have this curve that goes about around here. Okay. So we got this curve there. Okay, so you have this curve gamma. So gamma is this curve that's inside G, but it encloses Z naught with a positive orientation, and it's simple closed, so it starts here and ends here. It starts and ends at the same point. Okay, now if you were to take the integral, so let's also suppose that f of z, if we expand f of z about z naught, so I'm going to do it this way. So in a Laurent series. No, I'm going to do it this way. Right on that. Okay, and so we have c k over z minus z naught. So expanded about this point here in a Laurent series. Like that. Suppose it's able to be expanded like that, and we're going to figure out what these constants are. Okay, then the integral around gamma of f of z dz is equal to c negative 1 times 2 pi I. Okay, so this is what this corollary says. This integral is 2 pi I times c negative 1. Okay. Okay, so I wrote it backwards. Okay, so sorry about that. It's 2 pi I c minus 1. Okay, so let me explain briefly why that's the case. It's because of this. When we expand that out, so it's written this way, but let's write it this way though. So we can start back at c minus 3, and that's going to be over z minus z naught to the third power. And then you got c minus 1 over c minus 2, I'm sorry. Z minus z naught to the second power. Okay, so that's how that works. And then there's then you got the famous c negative 1, which is this one. And then you have c0, and then you have c1 times z minus z0. And then c2 times that squared. So you keep on going. So you got all those terms. And we discussed this before, that this one is just holomorphic. So that's going to be 0 when you take this integral. This is also going to be 0. Everything here is going to be 0, right? And then back here, everything over here is going to be 0 because this is squared. And that's going to be 0. Everything here is just going to be 0. And then by Cauchy's integral formula, it's just going to be 2 pi I times this numerator.